Good evening and welcome to PyData Manchester. Thanks for joining us for our September edition of PyData. Getting into autumn, a little bit dark, but we've got a great show lined up for you. Sara Robinson from Google is going to be talking about how we can design AI in appropriate ways in responsible ways to try and alleviate bunch of different issues that have been coming up, especially, and a lot of them have been coming up in tech and the news recently around ethics and that kind of stuff. So let's dive straight in. So as you know, I'm John. I'm one of the volunteers and on the Code of Conduct response team. Joe is very kindly doing the streaming. Jennifer and Sean will be in and around the comments and Slack to try and help answer questions, pass on questions to Sara, and generally just be helpful. Of course, we do have a code of conduct, and it's important, even while we are remote, that people make sure we abide by it. PyData is a professional environment, so try and behave professionally. If we've got any issues, then contact any of the organisers on Twitter or Slack, and we've also got the anonymous support form here in case you want to make an anonymous complaint. So friends of PyData Manchester, Open Data Manchester, I believe, have got an event coming up on the 22nd. Wait, is that tonight? They've got an event coming up soon anyway, as they usually do. Herpless Data as well have got another event. Python Northwest, I believe, the third Thursday of the month. But yeah, I believe these are the events still going during this during the lockdown or the pandemic, whatever. When we're not doing live events, we've also got the PyData podcast that we've recorded recently, so they're available on all good podcast platforms. So on your Apple Music or your Spotify, just search for PyData Manchester. If you've got any announcements, so if you've got a job you're looking to hire for, or if you're looking for a job, pop into the Slack in #jobs. Or if you've got a meetup you'd like to give us a shout out for, then we're happy to do so. Or any other general announcements, pop into the Slack. If you want to get involved, then again, whether it be as a speaker, as a podcast guest, or a sponsor, tweet us either at PyData Manchester or any of the organisers. All of our Twitter handles are on the PyData Manchester About Us page, little link, so you can find us in there. Similarly, you can message us on the meetup as well. We want to thank our sponsors for making this event possible. So Horsefly Analytics, Cathcart Associates, and of course NumFocus, who kind of make all of PyData, not just the meetups, but the code as well possible. As I mentioned earlier, we've got Sara Robinson from Google, who's going to be talking about design patterns for responsible AI. So I will hand you over to Sara now. Oops.
Thank you, John. Can everybody hear me okay?
Yeah, I can hear you just fine.
Okay, awesome.
Should have stopped my screen share, so you can go ahead.
Yep, I will go ahead and share my screen. Hello, everybody. Thanks to PyData Manchester for having me. It's great that I can, travel around the world without leaving my home office. So I do miss visiting the UK. I used to travel there quite a bit. So this will have to do for now. Can you see my screen? I'll make it full screen once we're good.
Yeah, that's fine.
Okay, awesome. So as John mentioned, drop your questions in whatever channel you're using to view this, and I will definitely take questions after I'm done. So with that, I'm gonna go into full screen. So hey everybody, I'm going to be talking about design patterns for responsible AI. My name is Sara Robinson. I'm a developer advocate on the Google Cloud team based in Cambridge, Massachusetts, the other Cambridge. If you don't know what a developer advocate does, our job is essentially an external facing engineer trying to get developers, data scientists, ML engineers excited about all the different machine learning products that we have on Google Cloud. So I do that through presentations, demos, demo code, videos, blog posts. Another important part of the job is taking feedback from the external community, so that's all of you, and channeling that back to our product team. So if anybody has feedback on any aspect of Google Cloud, specifically machine learning, since that's where I focus, things you like, things you don't like, pass it along to me. You can find me on Twitter. I'm srobtweets. Just send me a DM if you've got any feedback. And I also blog at sararobinson.dev. So with that, let's dive right in. I'm going to be covering a few different things today. First, I'll talk briefly about what design patterns are, and then I'll set the context by defining what responsible AI is. And then I'll dive in. So the bulk of the presentation will be focused on some of these patterns. And I always like to risk it all with some live demos. So we'll get into live demos towards the end as well. So to start, what are design patterns? So design patterns are defined as formalized best practices around common problems in software engineering. And so why are we talking about design patterns here? Well, I co-authored a book with two of my colleagues at Google. It's going to be released in November. November 3rd, I believe, is the date. We're super excited about it. It's available for pre-order at the link on the slide. And you can follow one of my co-authors, Lack, on Twitter as well. I'm pretty active tweeting about machine learning things. So we wrote this book that includes 30 different design patterns related to all aspects of the machine learning workflow. So in this talk, I'm going to be highlighting the design patterns that we cover in the book that are specifically related to responsible AI. But if you're interested in any other patterns related to, data formatting, training, scalably serving models, definitely check out the book. Just a quick preview of this diagram that is in our last chapter, which is our summary chapter, of all the different patterns that are covered here and kind of how you can use them together. It's pretty small, so you probably can't read the whole thing, but essentially the chapters are organized by different phases of a typical machine learning workflow. So we start with data representation, and then we end with responsible AI, which is what I'll talk about today. Okay, so now that we know what I mean by design patterns, let's dive into responsible AI. So responsible AI is essentially the practice of ensuring that machine learning models don't reinforce unfair bias, and that AI benefits everyone who is using it. So responsible AI is an umbrella term that encompasses a few different specific concepts. And those specific concepts are fairness, explainability, privacy, and security. And in a number of reports, responsible AI or issues with ethics have been cited as a really important reason that companies have abandoned using AI at all. So responsible AI is just a really important practice to take into account as you're building and deploying machine learning systems. And I'm going to talk about some ways that you can make sure that your models are, behaving in a responsible way that benefits all stakeholders and model users. So at the end of the day, responsible AI really leads towards successful AI because when you build ML systems that are fair, that you can explain and summarize to other, external stakeholders, your AI systems will be more successful. So just to summarize, responsible AI includes these 4 sub areas. I'm going to be focused mostly on fairness and explainability. I'm not going to get into privacy or security when I talk about these patterns. So just to introduce the different patterns that I'll be covering. The first is Heuristic Benchmark. And what this is a good starting point that you can use for summarizing your model as you're initially developing it. So something that you can use as a comparison point to understand how your model is performing when you don't have a previous model to compare it to. Explainable predictions goes one step further to try to understand how the different features of your model are influencing that model's output. And then finally, fairness ensures that models are fair and treating different groups of users in an equitable way. So a lot of folks might confuse the terms fairness and explainability. I definitely did as I was, getting started in this field, and they are pretty related and integrated. So I just wanted to specify what the difference between these two are before I go a little bit deeper. So fairness refers specifically to implementing practices that ensure that models are treating different groups of users fairly. Whereas explainability is the larger process of understanding how and why a model is making predictions. So explainability could absolutely be used to uncover fairness issues, but it could also be used more generally. So an example where you might be using explainability, but not necessarily in a fairness context, is maybe you're looking at medical imaging to identify, different diseases in maybe an X-ray image or other medical image, and you want to understand, the pixels in that image that contributed in that X-ray that contributed to the model predicting, the presence of a certain disease. So that isn't necessarily fairness, but it is revealing, giving more insight into how the machine learning model is making predictions. So that's, how these different concepts overlap. So with that, I will go into the first pattern that I'm going to cover, which is called Heuristic Benchmark. So to understand this pattern, I want to start with an example. So for this example, let's say you're building a model to predict the duration of a bike rental using some publicly available data on, city bike share systems. So you train your model and you find that the model's mean absolute error, MAE, is 1200 seconds. So that sounds great. But does it actually sound great? If, let's say, you're going to the business team that gave you the task of building this model and tell them that the MAE is 1200 seconds, it's going to be hard to explain what that means and if that's good or bad if you're just providing that one piece of data. And this is the first time you built this model, so you can't say, oh, this is an improvement from 1500 seconds in the last version. So the heuristic benchmark pattern essentially advocates for developing a simple point of comparison that you can use to summarize your initial model more effectively. So some good benchmarks could be a constant value. Maybe it's just the overall balance of your data set, So if you have a data set where you're doing binary classification and let's say 60% of your data contains the positive class, whatever the comparison task is. Ideally, your model should be able to have accuracy better than 60%, since the 60% would just be like a random guess of the data. A rule of thumb, another common approach could be using the mean, median, or mode across a subset of your training data set, whichever makes sense. Another benchmark might be human experts. So in the case of the medical imaging example that I cited before, you probably want to compare your model to how an expert would classify a specific image, and then use that as a comparison to see, can your model do better or just as good as that. It's not necessarily, this benchmark isn't necessarily determined by machine learning. So a lot of times folks will train a simple linear regression model as an initial model or a baseline. This is definitely something you can do, and it works in a lot of cases, but it's not always the best as a heuristic benchmark, because it isn't always easy to explain, and a linear regression model might not be the best choice for your task. So it's usually better to just choose something simpler when you're going for this this point of comparison. So back to our bike example, what we could use as a benchmark is we could say, what is the average duration given the station name and whether or not it's a peak commute hour? And take that value for a particular data point and see how does our model performance compare to this? Is it better, worse? And that's a point of comparison that's pretty easy to summarize to somebody else and explain, how our model compares to that point. So that's kind of an overview of the heuristic benchmark pattern. Whether you should use this, I developed a little flowchart. So if you already have an operational model or an operational best practice in place, you don't need to use this. You don't need a heuristic benchmark. You should use whatever that practice or model is that you've established as your benchmark. But if you don't, then this pattern can be a great starting point. So next step would be to choose your heuristic, train a model. If you're happy with that model, when compared to the heuristic you've chosen, then you can put that initial model into production. And then as you continue to iterate on that model, those future versions will be then compared to your initial model. So that'll replace your benchmark, your heuristic benchmark. If you're still not happy with your model, you can continue iterating, keep that benchmark, or maybe try a different one until you have something you're happy with that you're ready to deploy into production. So this pattern provides a really good starting point as you're building machine learning models, so that you're not, doing this in a vacuum, and you have points of comparison for the models that you're developing. So the second pattern that I'm going to talk about is called explainable predictions. And before I get into this pattern, explainability is kind of a loaded term. It evokes a variety of different concepts depending on your role and which part of the machine learning process you're thinking about. So it could be related to governance, transparency. And when I talk about explainability here, I'm specifically referring to explainability of machine learning models. So when we think about explainability, it's important to think about the different types of model stakeholders or model users. And here I've divided that into 3 different groups of people. So the first is data scientists, folks that are building the machine learning models. Probably most of the folks on this call fall into this first category. So model builders, ML engineers that are deploying models, and they might use explanations to ask, why isn't my model performing? Can you explain, this strange behavior that I'm seeing on a small subset of the data, and how can I use this information to improve the model and make it better? The second group of users is what I'm referring to as end users of ML systems. This also probably includes everybody here, since this refers to, this could be different types of people depending on the model. So maybe you're benefiting from a model that is recommending the next product you should buy. Then you're an end user of an ML system, or maybe a medical practitioner that's using the results of a model to make a diagnosis. That's a different type of end user. So this group of folks would use explanations to ensure that they can trust the model's output and provide them more data on how they should respond to the prediction. And then the final group is what's referred to as public stakeholders. This could be people both inside and outside your organization that are involved in regulatory and compliance standards for machine learning models. So this group of people wants to know, is the model safe and fit for purpose? Does it comply with regulations that are in place in the industry, whatever industry it is that you're deploying that machine learning model for? And then just some examples of actionability, how these different groups of users could use explanations to take action, either in improving the model or making decisions from model outcomes. I won't read through them all, but you can see them here. And I'll definitely share out the slides after to everybody who's on the call. So next I want to talk about what form explanations can take. Here I'm looking specifically at one type of explanation called feature attributions. I'll talk a little bit more about what that means shortly. So the form that explanations take really depends on the type of data that you're working with and the type of data you use to train your model. So it's going to vary pretty significantly for image, text, and tabular models. Those are the 3 types of data that we see most often. So that's what I'm going to focus on here. So for each of these types of models here, I provided some examples of what explanations look like. So for image models, one way that you can get explanations is through what's called pixel attributions. So this shows you the pixels in an image that contributed to that model's prediction. So in this case, this is a model that's, I think, trained on the ImageNet data set. So just, some higher level generic general labels applying to animals, plants, food, etc. So the pixel attributions that we're seeing in the two images on the right are explaining why the model predicted the label husky for this image. These are just two different approaches to showing pixel attributions. I'll talk about both of those approaches a bit more when I get to the demo. For text models, explainability will tell you the words in the text that contributed to the model's prediction. So in this case, we have a sentiment analysis model that's predicting whether or not a text document has positive or negative sentiment. And in this example, it looks like the model's relying on the words not and love to make its sentiment score prediction of 0.9. So, high positive sentiment. And this is an example of where we might use explainability to uncover fairness issues. So these are the correct words to be focused on in a sentiment model, in my opinion, because these are the most emotive words in the sentence. The sentiment of this sentence, or the predicted sentiment, shouldn't change if we replace cake with something else, like cookies or cupcakes. If instead the model was focused on that word and the sentiment changed based on the subject, then that might be a sign of that our model is not performing correctly. And you can imagine how that might play out with a more controversial human-centered data set, where we wouldn't want identity terms to influence our model's predicted sentiment. And then finally, with tabular data. So tabular data is types of data that you might find in a spreadsheet, numerical and categorical data specifically. So in this case, you get an attribution value for each feature in that model to indicate how much that feature influenced your model's prediction. So this is an example of a model that predicts the duration of a bike trip in minutes. And here we can see for one particular example, which features are most important. And attribution values can be positive or negative. What you want to focus most on is the magnitude or absolute value of that feature attribution. So in this case, the distance of the trip caused the model's predicted duration to decrease by about 2.5 minutes, followed by the start time also caused the predicted trip duration to decrease. So yeah, again, attribution values can be positive or negative. So in the book, we provide a few different approaches for explaining model predictions, both open source and cloud-based solutions. Today, I'm going to talk about some solutions for explaining models on Google Cloud, since I work on Google Cloud. And so right now we have a couple of different approaches for using this product called Explainable AI on Google Cloud. So first, this diagram, this pyramid diagram, is meant to just show most of the different machine learning products that we offer on Google Cloud, organized by their level of abstraction. So the products towards the bottom are targeted more towards data scientists, ML engineers, people that might have a bit more machine learning expertise. And these solutions are related to custom models, so models that you build yourself and need infrastructure for training and prediction. The products towards the top are targeted more towards application developers that might want to integrate machine learning into their applications, but might not have as much ML expertise. So the products that I starred are all the ways that you can use Explainable AI. So I'll start with AutoML Tables. So AutoML is a tool that lets you train custom models without requiring you to write any model code. And AutoML exists for different data types. So there's AutoML for image data, text data, translation, sentence pairs, videos, and tabular data. So right now, when you train a tabular model in AutoML, you get access to explanations by default, and I'll show a demo of that shortly. And then for TensorFlow models that you're building on your own, you can use Explainable AI in two ways. One, through our hosted Jupyter Lab solution, and I'm going to demo that shortly as well. And when you're using it through there, there's an SDK that comes pre-installed in AI platform notebooks that you can use, which lets you get explanations on models without having to deploy them. And then AI platform prediction lets you get feature attribution values back from deployed models, so models that you have in production. And I touched on this before, but there's many different types of explainability. And what I showed in the previous slides with the image, text, and tabular examples, that's just one type of feature attribution called, or that's one type of explainability called feature attributions. There's other types as well, and they're typically split into two categories. So the left is what's called post-hoc explainers. And this refers primarily to explaining more complex models like deep neural networks, where you look at the relationship between a model's features and the prediction output, but you're not necessarily looking at learned values like model weights. Whereas on the right side, the models that are interpretable by design, these typically refer to models with simpler architectures, like linear regression models, decision trees, models whose learned parameters are explainable to an extent on their own. So in a linear regression model, those learned weights can actually be used on their own to explain the relationship between features and a model's prediction. Whereas the learned weights in a hidden layer of a neural network are not really useful in that regard for explaining models. So that's the main difference. We recently released a solution called TabNet, which applies here to models that are interpretable by design for explaining tabular models. I can provide a link to more information on that after, but our cloud-based, most of what I'll be talking about today relates to feature attributions. So with that, let's get into some demos. I'm going to show two demos. First is an AutoML Tables demo of a fraud detection model that I trained and using explanations to understand which features are most important in that model. And then the second demo I'll be showing using our notebooks product, explaining a TensorFlow model, or two different types of TensorFlow models that both do image classification. So with that, I'm going to go to the demo and let's see. So I'm going to start with this AutoML Tables demo and let me go back to full screen. So I've used a public data set from Kaggle to train this model. This is the AutoML Tables UI for those of you that haven't seen it before. So the way it works is you import your data and AutoML can infer the data type. You can change it if it doesn't infer it correctly. And you specify the target column, the thing you want to predict. A quick note on the data set. So the data set is using real credit card transactions, but they obscured all of the feature names. So there's about 30 features in this data set. The original data set, all of the features are called like V1, V2, V3, all the way through like V28. I thought that was kind of boring, so I made up my own feature names. So it's still the original data set, the real data set. I just changed the feature names. So if they sound kind of silly, that's because I made them up just to make the demo a little bit more engaging. So once you have ensured that your data looks right, you can go over here and train a model. You tell it how many compute hours you want it to use for training, and you can also specify some advanced options. I'm not going to train a model now, but for this particular example, I chose to maximize model performance on the least common class. In the case of fraud detection or any anomaly detection, you're going to have typically a pretty imbalanced data set, which we definitely do in this case. And you can check out this data set. It's on Kaggle. It's also available in BigQuery. So this data set has about 500 examples of fraudulent transactions, but I think around 250,000 examples of non-fraudulent. So you're dealing with heavily imbalanced data sets. AutoML can help you solve for that by just checking this box to maximize performance on the less common class, which in this case is fraud. So moving on to the explainability piece of this. So once your model's trained, you'll get an email that training completes, and then you get access to this evaluation tab, which has some metrics on how your model performed. For fraud detection, especially, or any imbalanced data set, we really want to look at the confusion matrix because this will tell us how our model's performing for each class. In this case, like accuracy is actually not a great measure. We see 97.9%, which sounds really good, but what we actually want to look at is, especially in our less common class, how's our model performing? In this case, AutoML was able to achieve, in my opinion, pretty impressive accuracy given how imbalanced the data set was. I also did some downsampling on the original data set, which is why you noticed, if you noticed before, that there was only I think 4,000 examples used for training. But anyway, this looks good. This means that from our test set, our model was able to correctly identify 88% of the fraudulent transactions correctly, which is pretty good. And then we get, this is one of the explainable AI features that you get in AutoML Tables for the test set. So overall, across all the predictions made in your test data, which features were most important to your model? So in this case, it looks like whether or not there is a smiley face in the signature is the most important. Again, I made up these feature names, but you get the idea. So here we can see at a global model level, which features is my model relying on most. And for models that have a lot of different features like this one, we might be able to use this data to say, okay, could we maybe remove some of these features and go back, train a new version of our model and see if that model does better. And then another type of feature attribution that you'd want is instance level. So this tells us overall for our model which features are most important, but what we also want to understand is for an individual prediction, how did the features for that particular example affect the prediction? And AutoML Tables provides that as well. You can get them through the API, which is most likely what you'll do if you're dealing with a deployed model, but a quick way to test it out is through the UI, which I'll show here. So here, AutoML Tables just drop some random feature values in here, which is what I'll use. And if I check this feature importance box, when it runs my prediction, I should get feature importance values here. The feature importance values are pretty low in this case because our model predicted, in this case, a 99% chance that this was not a fraudulent transaction. And you can see which values push the model's prediction down or up. One concept that I'll touch on briefly is what's called a baseline. So you notice I've talked about, especially for tabular models, all of these different attribution values, like something maybe push the model's prediction up 2, down 1. What are all these relative to? And so all of those attribution values are relative to what's called your model's baseline prediction. In AutoML Tables, it uses, I believe, the median across all of your features as the baseline prediction. So for this particular model, we have just one baseline prediction. So what does my model predict when I take the median of all of the different feature values? That's the baseline prediction. And so that's what all of the different feature attribution values will be relative to. If you're using AI platform to deploy a custom TensorFlow model, you can actually specify what the service should use as the baseline, or you can use the defaults. So that is my AutoML Tables demo. I'm going to go into my AI platform demo. And to do this, I'm going to use a notebook. So this is our hosted notebook service. Just quickly, I'll show you how you would create a notebook instance. I'm not going to create one now, but you can customize which frameworks are pre-installed, the size of your instance, things like that. So I already have a notebook open here. And so in this notebook, I'm going to show you two different models. And I'm using our Explainable AI SDK to get explanations. So what I want to emphasize here is that when I get explanations on these models, I didn't have to deploy the model to get an explanation. I just have the model, the exported model assets in this notebook instance. So in this example, I'm using a model that I just trained on the ImageNet dataset, which is right here. So my model assets are here. I'm pointing the Explainable AI SDK at these local model assets, and I'm going to explain this jellyfish image. So for those of you that aren't familiar with ImageNet, it's a data set with tons and tons of labeled images that's commonly used for transfer learning, but you can also train a model just on that data set on its own. And that's what I did in this case. So ImageNet has 1,000 different image labels associated with it. One of them is jellyfish. So I just chose to see if our model could predict this image correctly and then get explanations for why our model hopefully predicted jellyfish for this image. So the SDK has this method available within notebook instances called load model from local path, which I did here, passed it that local model path. And these are the explanations, the pixel explanations for this particular image. I also want to load the key here. So this is a specific explanation method that we offer for images called X-ray, which I specified here. And what X-ray does is it gives you region-based pixel attributions. And so here we can see that the regions that are highlighted in bright yellow were the most important signals to our model for making this prediction. And then as we move towards this dark purple color, these were the least important regions in the image. So what the SDK returns is it tells us, first of all, what label did this predict, which this corresponds to jellyfish, which is good. I loaded the labels up here. It's 96% confident that this is a jellyfish. And here we can see the regions that cause the model to predict that image, that label. And so essentially here, we're just using explanations to ensure that our model is understanding the shape of the image, picking up on the right signals. So in this case, it looks like our model is doing a good job. Some red flags we might want to look out for is if instead we saw bright pixel regions in random spots around the image, in the background, for example, or just areas that didn't make sense. That might be a sign that we need to go back and improve our training data to maybe provide more varied examples for each label, or maybe change the model architecture, or the type of model we're using for this image. But in this case, it looks like our model is doing a good job. So that's a good sign. Explanations have verified that. Without explanations, we don't really, all we would get is this 96% value. So we would see that our model was 96% confident it was a jellyfish, but we wouldn't really have any insight as to why it did that. So that's another reason that explanations are really useful. Just help verify that your model is performing as you expect it to. The second image example I'll show you is a model that I trained on a chest X-ray data set, which I also saved this model here. And this is a data set that is also available in Kaggle if you want to play with it. I want to emphasize for this demo in particular, the focus is not on model quality. So the model that I trained on this data to identify whether a particular condition is present in these X-ray images, it's not the best model. So just, take it with a grain of salt. I'm mainly highlighting the tooling around model explainability rather than the quality of my image model for this example. So here's the explanations that it generates on this image. And an important feature of the Explainable AI service that I want to highlight is it returns this approximation error value. In this case, our approximation error is 24%. And the general rule of thumb is that if the approximation error exceeds 5%, you may not want to put so much trust in those explanations. It's likely pointing to something you need to change, whether it's the data that you use to train the model architecture itself, or maybe the particular baseline that you chose for this model. For image models, a common baseline image is just a solid black and solid white image, both or one or the other. That's what's referred to as an uninformative baseline. But if your images contain, a lot of black or white already, that might be not the best baseline. So you might want to go back and pick a different one. So just a quick note that, your explanations are only going to be as good as the model you train and the data that you use to train it. If you train your model on, a data set that doesn't reflect the population that's going to be using your model, or you don't train your model for enough time, the explanations won't be able to uncover, any additional insights. You need to make sure that you're using, high quality data sets and models, and then you can put more trust in your explanations. So that's kind of why I mentioned that, I didn't train a very high quality model here. Explanations were able to identify that and point out that the error for this particular model is high. So just two examples. Yeah, go ahead.
Can you just zoom in a little bit so the code's a bit easier to read?
Oh, yes, sorry.
Sure.
How's
No worries.
that?
That's better, thank you.
Okay, let me just scroll up a bit since folks may not have seen all the code. So the main thing to highlight here is that I'm using our Explainable AI SDK, which comes pre-installed in these notebook instances. And then I'm pointing it to my model directory, and I've exported, I've already trained these models, but the exported model assets are just here in the notebook instance. So they're not deployed anywhere. I'm just connecting it here to get the explanations. And then the method that I want to highlight is this load model from local path, which is what I'm using to get explanations. And then these were the explanations on the jellyfish image. One more thing I want to highlight here is once you have used this SDK, if I don't know if anybody noticed, but when we go into these directories, this explanation metadata file was generated when we pointed the SDK to our model directory. And this is some metadata that the explanation service needs to generate the explanation on your model. And so once you've generated this file with the SDK, you have everything you need should you want to deploy this model and get explanations on your deployed model. So I'm not going to deploy it now, but all you would need to do is just copy this directory to a Google Cloud Storage bucket. And then this is one way you can deploy your model. So this is deploying it through our Google Cloud CLI right here. So you would just run this deploy command, point it at the directory with your model assets, and tell it which explanation method you want to use. Since we're a bit low on time, I want to make sure we have time for questions. I'm going to go back to the slides and talk about our third pattern, which is fairness lens. Before we get into the pattern, I'm going to just talk about a quick example. So let's imagine that your organization is building a fashion classification model to classify different images with different types of clothes and accessories. And you're in charge of collecting all of the shoe images for the model. So just think about when you think of a shoe, what's the first thing that comes to mind? For the sake of this example, let's imagine that you live somewhere that is warm all year round, and so you wear sandals pretty much every day, and so does everybody else you know. So you could go about collecting a bunch of diverse images of sandals and test your model on some of those images and find that it's performing really well. But then you go to deploy the model and you have people from all over the world using it, and it is, not surprisingly, it's not finding shoes in images that clearly have shoes, like sneakers and high heels, things like that. So that's, obviously an oversimplified example. But the point I'm trying to illustrate is that there's obviously, as we can see through these emojis, lots of different types of shoes that you should have accounted for when you're collecting that data set, rather than just the one that you're familiar with. So this is one type of data bias that you can have in models. This is referring to data distribution bias. But there's a lot of different types, and people often are quick to associate bias as a bad thing. It's not necessarily always bad. There is naturally occurring bias, and then there's harmful data bias. So an example of naturally occurring bias might be the fraud detection example I showed, where there simply doesn't exist more examples of fraudulent transactions in that example. So I'm going to have to use techniques to account for that. I can't try to go collect more fraudulent examples because there just aren't any. So there's a lot of techniques, and there's a couple different patterns, which I am not covering in this presentation, but are covered in the book, that talk about how to account for naturally imbalanced data sets. The fairness pattern mostly addresses issues of harmful bias in data sets and how you can account for that. Not just data sets throughout the machine learning process, but here I'm referring specifically to data bias. So the shoe example was an example of data distribution bias because we didn't have enough examples of every type of shoe that we should have. So we had a lot of sandals, but then none of other types of shoes. That's data distribution bias. Data representation bias occurs when you do have a balanced number of examples for every possible variant of a particular type of data. there's bias in those particular examples. So let me go to an example because it's way easier to understand with an example. So let's say we have we're training a model on restaurant review data to predict, whether a review is positive or negative. So let's say that we've identified, all the types of restaurants and cuisines that we want to gather reviews from, and we have an equal number for every type of restaurant that we've identified that we want to collect data for. So our data is distributed equally, but let's say, for example, that the majority of our seafood restaurant reviews have very positive reviews. So let's say like 90% of those reviews are positive, whereas maybe our vegetarian restaurants, only 20% of those reviews are positive. So we have an equal amount of reviews for every category, but the representation bias is going to significantly affect the model and how reviews of different types are classified. Experimenter bias refers to bias that occurs in labeling data. So oftentimes, data sets can be very time consuming to label. So it's common to outsource that labeling task. But many times that labeling can be subjective. So if we look at a text sentiment analysis example again, maybe the sentence like, I'm doing fine. Depending on, where you are in the world, just, what you're used to, you might think that's a positive sentiment, but somebody else might think that's an extremely negative sentiment. So it's important to be aware of cases where labeling data can be subjective, and to take that into account to make sure you have a diverse representation of the types of people that are labeling your data. But in addition to data bias, bias can affect your ML system at various phases throughout an ML workflow. So I touched on collecting and labeling data. Bias can also occur at many different phases, including the metrics you choose to evaluate your model on. So remember in the fraud detection example, I said that accuracy would be a bad metric to choose for that model. So that's one example. Let's say that I did use accuracy in that case, and in that case, accuracy would not have been a good metric to choose. So that's just another way that bias can find its way into the ML system at different points. So just something to be aware of as you're building a model, that you can't associate bias with one particular part of this ML pipeline. It can find its way into any step, and just to be aware of that and use that as you continue to iterate on your model. Again, in the book, we talk about a number of different tools for addressing fairness. And here I'll highlight one. This is an open source tool called the WhatIf Tool. It's developed by a team at Google called the PAIR team, People in AI Research. And the WhatIf Tool is a visualization widget that you can run within Python notebooks. You can run it in Colab, you can run it in local Jupyter notebooks, TensorBoard, many different places. And so it lets you evaluate your model, look at different data points, and also evaluate your model by different slices of your data. So this is just one screenshot of using the tool to look at a binary classification model trained on the US Census dataset. And the WhatIf Tool, as I mentioned, it's available on many different platforms. So you can run it in Cloud AI platform notebooks, which I'll show in a moment, in Colab, TensorBoard, and it supports a bunch of different types of analysis. So you can do what's called counterfactual analysis, which I'll show. You can also slice your data by a number of different fairness measures, as well as get partial dependence plots. It also lets you compare two different models trained on the same data set. So let's say I train a TensorFlow model and a scikit-learn model on the same data, and I want to compare how the model is behaving for each of those models. I can do that in the WhatIf tool as well. And you can connect it. You don't have to connect it to a cloud model. You can connect it to a model that's available locally from wherever you're running the tool. But it does have an integration with AI platform and with Explainable AI. So if you connect it to a deployed model that has explanations enabled, you can get attribution values, and you can visualize them within the tool. So with that, I'm gonna, go to a demo. John, how am I doing on time? I forgot how much time we have total. Do I have time for this demo?
Yeah, we're in no rush. You've got as much
No
time as
rush. Oh, okay, great. Okay, so in that case, I will show a quick demo of the WhatIf tool using a different notebook. So what I'm showing here is I have found a data set on publicly available data on mortgage applications in the US. And I trained a model to predict whether a particular application would be approved. The data isn't made available for the purpose of building models, so this is just used for demo purposes. So I am going to make sure that this is still active. So this is the code that I use to load the tool. And when I load the tool, I pass it a set of data points with their ground truth values. So in this example, I am sending the tool 500 examples from my test set. And I am connecting it in this case to a model I've deployed on AI platform. In this case, an XGBoost model for predicting whether a specific mortgage application will be approved. So this is what we get in the WhatIf tool. And what we see here are all of our test data points visualized. Let me make this a little bit smaller actually, so we can see the whole tool real quick. Sorry, this isn't bigger. I'm trying to make that bigger and my computer is not working with me on that. So what we see in the legend are the blue data points are applications that were approved. The red data points are applications that were denied. And the y-axis shows our model's prediction confidence. So data points that are clustered towards the bottom, these are pretty high confidence that by our model that these are not approved, whereas data points clustered towards the top show data points that have a high confidence of being approved. And then ones in the middle, our model is less confident on. So this particular model outputs a single value between 0 and 1, indicating the percentage likelihood that a particular application is approved. So we can click on an individual data point, and here we can look at all of the different feature values for this data point. And one thing that I can do in this tool is I can change feature values and see how that affects the prediction. So in this case, since this is an XGBoost model, all the feature values needed to be numeric. So I created what's called dummy values, which basically takes a feature that originally was categorical, like for example, the agency that approved a specific application, or that a specific application went through. And then it converts it into what's called dummy columns for each possible value for that feature. So I'm going to change the agency associated with this application. And I'm going to rerun the prediction. And then use that to see. I might need to refresh the tool. I don't think I did that when I initialized the notebook. Sorry about that, folks. Live demos, you never know how they're going to go. One sec. I'm going to reload the tool. Okay, let's try this again. So I'm going to click on a data point. I will change the agency associated with this particular data point. Oops. And let me rerun the prediction. Hold on. Okay, there we go. That time it worked. So changing this particular feature didn't influence our prediction a huge amount. Actually, it did cause the percentage confidence that this application was denied to increase by about 11%. So it actually did affect it quite a bit. So we can use this to just get a better idea of how our model is performing, both at a data point level and at a higher level. I mentioned in the slides counterfactual analysis. So what counterfactual analysis does is it lets me take a data point, let's say this one, and if I toggle the nearest counterfactual, what it's going to show me is it's going to show me the data point that has the most similar features to this originally selected data point, but resulted in the opposite prediction. So I'm seeing both data points here, and then in green, it'll show me where these two data points differed. So counterfactual analysis can be really useful. A fairness aspect of this tool, which I want to highlight, is when you go to this performance and fairness tab, you can slice your data across different features. So in this case, I'm going to slice my data on loans that were for home purchases. Okay, so this feature has two possible values. 0 means that the particular application was not for a home purchase. 1 means that a particular application was for a home purchase. So here we can see, first of all, that our model has a slightly higher accuracy on loans that were for home purchases. And if we look at the percentage of data points that fall into this category that were predicted as approved, we can see that for non-home purchase loans, 51% were predicted approved, whereas for home purchase loans, a much higher percentage of those were approved. So this can bring to light some differences in how different slices of your data are being treated by your model. Maybe this is intended, but if it's not, and we want our model to behave in a more equal way across these different slices, we can apply these optimization strategies. So for example, demographic parity will, let's see, it means that similar percentages of data points from each slice are predicted as positive classifications. So if I click on this, notice that, oops, let me go back to that. This changed the threshold of when I should mark an application as approved. So what threshold refers to is the threshold at which you decide to predict this as a positive class. So the threshold that you choose is going to depend a lot on what your use case is. So if you, let's say you have a model that's predicting whether or not an image contains a cat. In that case, maybe if your model predicts higher than 70% confidence that it's a cat, then you want to show the user that it's a cat. Not a real high stakes situation. Probably not. Maybe it is. I don't know. In that case, maybe you're okay with 70% as your threshold. Say if confidence is higher than 70%, then we'll show the user that yes, it's a cat. In a situation with maybe a medical model, financial model, chances are you want your model to be very high confident in whatever you're predicting before you show the user that something belongs to that class. So these optimization strategies will change your threshold to account for different fairness metrics. And you can see what each one does by just clicking on this button here. So that's all I'm going to show for the fairness tab. What the features tab does is it just shows you how your data is balanced by different features. So remember, this is just for the 500 test data points that we sent it. We can see, how the data is balanced across different features. And you can actually use this tab of the WhatIf tool without sending it a model. So you can load up the WhatIf tool by just passing it data and not setting a model, and you'll get this tab. And it's just a good way to see, maybe even before you've trained a model, how balanced is your data? Is there more data that you need to collect for a certain feature? Things like that. Anything else that I missed here? Oh, you can customize all of these the visualizations on this tab. So I could scatter by whatever I want. I could color by, let's see, inference score instead. Or, I could color by different features in my data set. There's a lot of opportunity for customizing this data however you'd like. You can also bin the data. So I could bin it by home purchase, which is what I showed before. I'll change the color to inference label. And so then what this is showing is that, again, we're slicing by loans that were for home purchases and loans that were not. And we can see the percentage of each that were classified as approved by our model. So lots of opportunity to customize what you see here. So that's all I'll show for the WhatIf tool. I'm going to go back to the slides. And so what I've got left are some links. Again, if you want to pre-order the book, if you are interested in the design patterns I covered here and want to learn about more of them, you can pre-order the book, coming out in November. Super excited about it. If you're interested in the Explainable AI products that I showed on Google Cloud, the team wrote a white paper. It's a really great paper to read if you're interested in why we chose to use certain explanation methods and just a lot of the theory behind this. If you want some sample code for explainability, it's available here. Got more on the WhatIf tool, and then, a bunch of code labs. Code labs are just step-by-step tutorials for accomplishing different things related to all the different technologies that we have on cloud and beyond. I've written a couple of tutorials that are on here for both the WhatIf tool, explainability, just general AI platform tutorials. So if you just type in the search, any of the products covered here, you can find some step-by-step tutorials to help you get started with those. And that is all I have for the presentation. So thank you for listening, and I'm gonna go back to the meet. I think I'll stop sharing and I'll take questions.
Okay, thank you very much, Sarah. That's fascinating.
Yeah, thanks for having me.
There's a huge amount there. We've got quite a lot of questions, so I'll do my best to get through what we've got. Thank you very much for everyone who's popped a question into the various channels as well. So excuse me while I read these on my phone. So the question from Tariq Rashid. The top level objectives of responsible AI are presented here as fairness, explainability, privacy, and security. Where did this set come from?
That's a great question. So where did this definition of responsible AI come from? So Google has put out what's called AI principles. So a set of responsible AI principles, and it largely comes from that. If you just search AI principles, you should be able to find it. I can also share that out after. That was released, I believe, 2-ish years ago, just to ensure that as AI becomes more widely used, that we want to help people ensure that it's being used in ways that create positive implications and treat different groups of users equitably. So that's largely where that stems from.
Cool, that makes sense. So just a couple of questions around the SDK. So first of all, is it the same SDK that's used for text and tabular data?
Great question. The Explainable AI SDK, yes, you can use the same SDK for whatever type of data you're using. It'll just visualize the results a bit differently. So obviously for tabular data, it'll create, I think, a matplotlib chart with feature attributions. For image data, you can create what I saw before. So to clarify in the SDK, part of the SDK is open source. You can find it on GitHub. I should have included that link in the slide, but if anybody wants it and can't find it, just let me know. Send me a DM on Twitter. So part of the SDK is open source. If you want to use the SDK to generate the metadata that the service needs to get explanations on your deployed model, you can use the open source SDK for that. If you want to get explanations on a local model, that's the functionality that's only available within AI platform notebooks.
Okay, so just to clarify, so part of the functionality is available for anyone to install on whatever machine, but some of it is just on the AI platform notebooks.
Yes, exactly. Sorry if that was confusing. So getting explanations on undeployed models, that's the part that's only available on our platform. Still, I think that simplifies the process because if you wanted to iterate on a deployed model, you'd have to deploy a version with a different explanation method. And then let's say you decide you want to use a different explanation method, you'd have to redeploy the version and test it out. Whereas you can do that all from the notebook, just iterating on different variants.
Yeah, sure, that definitely speeds things up in terms of iteration. So around TabNet, which you mentioned briefly earlier, so does TabNet generate explanations or make it easier to create explanations from models created by it? So does TabNet generate? Sorry.
Let me find. I'm going to share the link to TabNet. 2 links actually, and then I'll do my best to answer the question. One sec.
Cool. Yeah, I mean, I should mention, we'll be happy to tweet out any links from the PyDataMCR Twitter account so people can find what you're talking about afterwards.
Okay, cool. So this is TabNet. It represents a different type of explanation method. So different research available on it. I'm going to share the link in the Meet. Feel free to share it out also wherever folks are watching. So that's the paper. And then this next link I'll share is how you can run TabNet on models trained on Google Cloud, a blog post announcing that. So all of the explanation methods that we offer on the Explainable AI product are based on publicly available research. So you can look up the papers on arXiv for all the different methods we offer.
Cool. That, I guess, brings us on to another question about, I guess, about the concept of explainability, of when you need to have a research, when an explainability method kind of needs an entire research paper to explain what it is and how it is, is it still useful if you can't explain it to a standard member of the public or a stakeholder, as you mentioned? Is that a trade-off you've got to think about?
Oh, that's a good question. So you're asking about like the complexity of each explanation method?
Yeah, pretty much.
Yeah, that's a really good question. So I guess that depends on the questions you're being asked about your model and how you're choosing to summarize it. So the end result, the output of these explanation methods is hopefully meant to simplify, how you summarize your model. Maybe that's, showing a pixel visualization or showing a bar chart of attribution values for a tabular model. In my experience, that's the format that most folks would be interacting with. But it's true, if people are going to be digging deeper and trying to understand, how those methods work and if they can trust those methods, then yeah, it probably makes sense to, either be able to summarize those research methods or choose something simpler. And that's again points to the trade-off between whether you want to be using, a more complex model like a deep neural net, using those post hoc methods, or if you train a linear regression model or something simpler like a decision tree, it's easier to attribute those explanations to the model architecture. It's a long way of answering your question.
No, I mean, that makes sense. I mean, I guess it always does come down to the context in which you're operating.
Mm-hmm.
So I've got a question from Rebecca. Even when machine learning developers see the value in fairness and explainability tools, selling the extra time and resource cost to managers and stakeholders is another matter. How can developers best advocate for incorporating these practices into their work?
That's a great question. So I'm assuming you're asking, like, how are you going to convince, as a data scientist, maybe you need to convince your boss that it's worthwhile to invest in these methods. Yeah. And one way that I think these are really important is, if you're just trusting your models to make predictions based on, maybe whatever metric you choose, especially with deep learning models, you really don't know at all how that model is making predictions under the hood and what features it's relying on. So in the image example, maybe it seems like on the images you tested on that your model is performing correctly, but it could be using pixels that really have no significance in making the prediction. So it provides a lot of transparency. I think that's really important into understanding why your model is making predictions, and it can also help your end users have more confidence in the model. So there's some cases where you might choose to expose these attribution values to your end user. At least for me, like if I'm being recommended something, maybe while I'm shopping, I might want to know why I was recommended that thing. So in that case, it is useful to in improving end user trust in the model. I'm going to be more likely to, to buy something again if I know like, oh, okay, this is why it was recommended to me. Totally makes sense. And it'll make me more likely to rely on those recommendations in the future. So I guess to summarize that, just the big benefit is in improving transparency and ensuring that different groups of users aren't being missed by your model.
Sure,
Great question, though.
Thank you. And thanks to Rebecca, because it was her question, definitely not mine.
Oh, thank you, Rebecca. Great question.
So from Oliver K, sorry if I'm mispronouncing that. Is there scope for an overall fairness score, or is this too subjective for an automated program to achieve? Hard rules maybe aren't always ideal.
Okay, yeah, I'm going to attempt to summarize the question. So the question was around, can you, at the outset of building a model, maybe set some overall fairness goals for it? Is that the question?
Yeah.
Is that useful?
I think I'll trying to, because rather than exploring the overall, all the various different ways in which one can explore the question of fairness, if there's an easily summarizable quantity we can give to explain or to pass on to other people who may not, or stakeholders who may not be invested in the model, but just be able to say, okay, this has a fairness score of 100 as opposed to these are the trade-offs and this is where it is fair and this is where it's less fair.
That's a really good question. I don't know of a metric for that exists currently, but my guess would be that depending on your use case, you might be able to define your own, taking into account the fairness pieces that are most important to your use case. So maybe you want to summarize the data set before you even go about training the model. Oh, actually, one thing I just thought of is a tool called Model Cards that Google released a few months ago, I think. Just search Model Cards. I don't know a ton about them. I didn't work on Model Cards, but I think what they're meant to do is just provide some facts for each model so that people that are using those models have a bit more data on what they were trained on. And they created Model Cards for some products that we offer, and machine learning APIs that we offer on Google Cloud. So I think that's one approach, but you'll probably want to create your own version of that metric. But that is a great idea, to taking your use case and then using that to figure out how you can better summarize fairness for your stakeholders, whoever they may be. Let me share a link to Model Cards. One sec.
Yeah, I mean, I think Model Cards is a really useful suggestion. We've kind of in the work that I do, we've used Model Cards to help explain and convey a lot of more complicated ideas to stakeholders, and just having it there and easily thought out has been a big improvement for us.
That's great to hear. Yeah, one thing they compare Model Cards to is like nutrition facts that you see on food. I just shared the link.
Yeah, thank you.
Yeah, so in the same way that nutrition facts are giving you more transparency and insight into what's in your food, Model Cards are kind of a way of doing that for machine learning models. Just shared a link out to those.
Yeah, thanks. Well, yeah, I'll make sure we tweet out all of these links that you shared in the chat, so everyone can see them. So we've got a couple of questions about the WhatIf tool. So some questions about what kind of model formats are recognized in the WhatIf tool, what different bias optimization approaches are in the WhatIf tool, where we can find the WhatIf tool, which I think you shared a link to that, to where we can find the WhatIf tool.
Yeah, I can paste the links from that slide in here as well. Okay, so first, what model types are supported? You can actually use the WhatIf tool for models built with any framework. It doesn't have to be TensorFlow. So you just need to provide a custom predict function to tell the tool how to get predictions on your model and analyze the result. So I used it in that previous example with an XGBoost model. You can use it with scikit-learn, pretty much any framework type. And it works. So right now, I think it works best with tabular models, but you can also use it on image models. They have some demos on their site showing how you can use it with image models. And one thing that I just thought of that I forgot to mention is the same team that built that recently released a tool specific for language models called LIT, the Language Interpretability Tool. I will also share out a link to that because I'm really excited about it. So you should check it out. Just
Cool,
shared a link to that GitHub.
And I think the last question, again from Rebecca, given all the tools and attention now out there about explainability and fairness in AI, what do you think the main obstacles and reasons why people still neglect these considerations around using these tools?
Another great question, Rebecca. Thank you. I think part of it is that it's still kind of an emerging area of research. So when machine learning was new, people weren't really thinking about this aspect at all. They were just thinking about, this new technology. What are the different types of models you can build with it, et cetera. As research advances, I think, and more people use AI, I think this is going to be a concern that more people are taking seriously. But there's still a lot of emerging research in the field. And as I mentioned, I only showed, for explainability specifically, I only showed one type of explanation, but there's a lot of others. Another type of explanation is what's called data-based explanation. So for a particular prediction, this type of explanation would point to an example in your training data set that was similar to the predicted example, and can help explain why your model predicted that example. So that's another type. So because it's so new, there aren't any, I think there's not like official, standards of how you should be explaining models. It's still a relatively new area that people are exploring. I think that's probably the biggest reason.
Sure. Like so many things in machine learning and data science, it's all still being figured out.
Yeah, things are changing, by the month. Always new versions of ML frameworks and libraries.
Yeah, sure. All right. Well, thank you very much for joining us, Sarah. It's been fascinating. I know I've learned a lot. I'm sure everyone watching has been. So yeah, thank you very much. And we'll make sure we tweet out all the links, and we'll keep everyone updated when your book comes out. Awesome.
Yeah, thanks for having me. And if anybody has questions, feel free to send me a tweet on Twitter. I'm @RobTweets, or send me a DM. Usually reply pretty fast. So thanks for joining and spending your evening here if you are in the UK.
Thank you very much. Thanks, everyone.